Hi there, students, and welcome back to this course in ABE153. This is our 8th lecture, and this is the last lecture that we'll talk about um, mechanics. Since we are already done with the discussions on both the static loadings and dynamics loadings and associated stresses, then we are now going on to the topic about failure theories and the factor of safety. When we say factor of safety, it's actually going or something like a feel that it's a design applications. Okay, so it's all about uncertainties and how do we deal with it. Okay, but before that, I'd like to mention that there are still some other topics that are important, but we haven't discussed due to time constraints, and those topics are the impact loadings and the deflections. When we say impact loadings, it's a sudden load or a sudden application of load, and we haven't or we didn't did computations regarding that. And another one is, as I've said, is the deflections. Although we haven't discussed the deflections, but in our ABE161 course, we talk about flexural members. I mean, for steel members, for steel structures, there are topics like, for example, flexural members, and we discuss the possible deflection or the possible failure of a flexural member. Like, for example, one is the lateral torsional buckling. Okay, so for example, if we load a member in flexure in basic strength of material course, we are just taught that when you load this flexural or this member in flexure, then what you get is a deflection, something like this, right? However, for steel structures or structures engineering, when you load this, it is possible that this cross section actually twists something like this. So that means that it's also a failure or something like, I mean, in a design standpoint, we need also to consider this. And you already know that this lateral torsional buckling only occurs because there's not much lateral bracings right here in the compression portion of the flexural members. Okay, and there are still many others, like for example the columns, actual members. So when you load this, then there's gonna be buckling and things like that. So the reason why I'm bringing this up is because if, let's say, you want to have a thesis about machine or equipment, then probably you should consider. I mean, I think, or I suggest that you also need to consider the deflection aspects of the machine design. Anyway, that's not our main topic, so let's get started regarding the failure theories and the factor of safety. Okay, so as I've said, a factor of safety. As I have said that the factor of safety is, or when we talk about factor of safety, we are actually talking about design applications. Okay, and it's all about uncertainties. That's how I describe it. A factors of safety is something like, or roughly, we can say that it's all about uncertainties. In what? Uncertainties in the design. And what are these uncertainties in the design? So we can have examples. We can have um, possible overloading, or load estimations. So for example, if we estimated a load, and the question is it really the load that the part will experience? during its service, right? So for example, if we design a shaft, so if we design a shaft and we estimated the load and we computed, let's say, the reactions and the stresses and stuff like that, but in actual service, is it the same stresses, or probably would it experience a possible overloading? Okay, so those that's one of the uncertainties in the design. Another uncertainty is the material, let's say material properties or or qualities. Okay, so what this means is that, or how I understand this is, let's say we have a steel, and let's say we have or that steel is specified as 250 megapascal for its yield strength. Okay, so SY is 250 megapascal for yield strength. Now the question is, or my question is it the same? Is it? I mean, is the strength, or is the yield strength of the part that you are going to use in the design, will it have the same value for the yield strength? Okay, is it 250 megapascal, or maybe it's lower? Okay, so there's gonna be discrepancies or differences. Then of course that's gonna be uh, that I mean we can consider that as uncertainty. Another one is the fabrication aspects. And this example is that, for example, or in the drawing or in the design intent is that, let's say we are going to load this part or this column in actual loading, and we design it that this load, or that this point load is actually acting at the centroid. Okay, however, due to fabrication aspects, like for example, we have a brace like here, a brace here, and another brace, and of course during fabrication, there's going to be welding on this part, and then another welding on this part, and we know that in welding process, there's heat involved, and therefore there's going to be a variation, temperature variation along this or across this part. And if there's going to be an even temperature distribution, like for example this one is hot or high temperature, and this one is low temperature, and if there's not much enough bracing, then there's going to be distortion of this part. Okay, so the distortion, uh, that's a that's a change in the geometry. So instead of having a purely straight part, then it could be that if there's not much enough bracing, then probably it's gonna be crooked, something like this. And the problem is that if you apply a load, so instead of this load is passing through the centroid of the section, it's not actually passing through the centroid of the section, and there's gonna be eccentricity. So because of the presence of eccentricity, then you don't actually just have you don't just have a natural load, but also a moment as well. So those are some of the uncertainties in the design, and there are still many others. So the question for a designer is that how do we guard ourselves from these uncertainties? And you already know in ABE161, the agricultural structures engineering, about the two approaches for this design. So one is the ASD, and the other one is the LRFD. And this one is the allowable stress or allowable strength design. Okay, but I guess although previously this is referred to as allowable stress design. They just change this to strength so that it's going to be the same basis for the LRFD. However, I guess for machinery design application, I think this is still the term that's being used, allowable stress design, and this one is referred to as the load and resistance factor design. Resistance factor design, right? And we know that this method right here, this is more statistical. It's an it's a statistical approach, and this one is a what is this? This is a conventional approach, and you already know the difference. And we did also sample problems or computations regarding this, but uh, although some of the machine design textbooks they have included this, I mean, it seems that they have included some portions or some pages regarding this LRFD. I mean, or they mention about the statistical approach, but in my opinion, there's not much data regarding or data regarding the use of this for I mean for machine design application as compared to the civil engineering applications. Okay, so for example, in the civil engineering applications, we have load combinations. What if, let's say, we have a wind load and earthquake load and live loads and dead loads that are, or whatever loads, in combination that are acting on the building or on the structure, then how do you work for it? Okay, so they have already load combinations, and they have data for the live loads and things like that. So for machinery design application, I haven't seen yet data regarding, let's say, a combination of static loads and, let's say, fatigue loadings or impact loads or whatever whatever parameters right here. Okay, so I haven't seen yet, so that's why we are not going to use this approach, and we'll just stick with this allowable stress design. Okay, so how does this factor of safety enter the equation? So we have this equation that n, this is the factor of safety, is just simply equal to the allowable stresses all over the applied stresses, right? And what that means is that for the allowable stress, this is, just imagine that this is our strength side in the LRFD, and this one is the load side, because the idea for the design is that if you have this part right here, let's say we have a part and we load this in tension, then and then usually for the design we don't want this part to fail. So if we don't want failure, then we can actually think, or we can divide this one in terms of the strength or the capacity. So it has a capacity or strength and the load that you are going to put on this part. So we have the load or applied stresses, right? So if the applied stresses is are greater than the strength or the allowable stress or the capacity, if it's more than the capacity, then that means that the material will fail. Okay, so typically we don't want our, I mean, when we say design, typically we don't want our part to fail. Okay, so here's our equation for the factor of safety. Factor of safety. But we can also describe factor of safety in terms of the geometric illustrations, because later on when we talk about failure theories, then it can also be an aid to refer to the diagrams. Okay, so typically we'll have a graph of, let's say, the principal stresses, or the maximum stress right here, principal stress maximum, and here the principal stress minimum. Okay, and we'll have some curves, or some curves like right here. For example, we have let's say this is SY, the yield strength, and we'll also have yield strength like right here. So here's our failure. This is what we call as the failure locus line. And what that means is that if you are beyond this, or if you are outside the failure locus line, then that's gonna be unsafe. And if you are inside, then you are in a safe region. Okay, so failure locus line, this is just an example. There's still many other, like for example curves, and we'll talk about that when we get into the topic on failure theories. But regarding this factor of safety is that this is the strength side. Okay, so our load side would be, let's say we'll have a load. Let's say we have a part, right, and we load it. Let's say we load it in a flexure, and we load it in axial, and also in torsion, and we computed for the stress state here. So stress state, that's something like the actual loadings experience at that point. Okay, and at that point, let's say we have a load point right here. So here's our load point, and that's the stress state, load point, or stress state, and the factor of safety is that we'll project a line from the zero, or from the 0 point, okay, to this load point, right? And of course we are going to intersect this failure line, and there's going to be a point right here. So let's say this is point O, and this is point A, and this is point B. So we can describe, or we can say that the factor of safety is simply the strength. So the line from this point O to that point A, that's OA, divided by the line from this point O to point B, because that is the load side and this is the strength side. Okay, so we can, let's label this. This is the load side, and here this is the strength side. So the strength could be in terms of field, or in terms of ultimate tensile strength, or in terms of endurance limit, and we'll discuss that in detail later. Okay, so the point here is that if this is the numerator and this is the denominator, then that means that we'll have a value of n greater than 1. Okay, so if n is greater than 1, then that means that we are safe. Okay, the more you are away from this, of course, the more that it's safe in terms of this concept of factor of safety. But of course, the more you are away from this, then practically there's gonna be another factor that comes into play. I mean, another aspect of design that comes into play, and that's gonna be the economics. Okay, so anyway, that depends upon the designer. Okay, so you can have, I mean, it's up to you if you want to have a factor of safety of, I mean, larger value of factor of safety. So that depends upon your design situations, and also the designers. So if we have n less than 1, then that means that the denominator is larger as compared to this strength side, then that's gonna be failure. Okay, so I'd like to show you one from one of our reference textbooks about this recommended values for a safety factor. By the way, this textbook is by Juvenal and Marshak, Machine Component Design, and there's a portion about the recommended values for a safety factor. So instead of computing, instead of computing the values of a factor of safety from the failure theories, then there are some ballpark values. It says here some suggestions for the ballpark values. Okay, so at least as a guide, okay, or some suggestions. So the point here is that we can have a feel or a grasp of understanding regarding the values or the range of values for the factor of safety. So it says here, like for example, if we have an exceptionally reliable materials used under controllable conditions and subjected to low stresses that can be determined with certainty, then typical values for the safety factor is 1.25 to 1.5. So let's move on to number 4. For example, we have a less tried materials, or for brittle materials under average conditions of environment, load, and stress, then the factor of safety actually increases 2.5 to 3. And for let's say we have a better known materials that are to be used in uncertain environments. So we have in certain environments or subjected to uncertain stresses, then the factor of safety increases to 3 to 4. And if we have repeated loads, then it says here that we can use safety factors from 1 to 6, but it says here it must be applied to the endurance limit rather than the yield strength. Okay, and we know that the endurance limit is far lower than the yield strength of the materials. And if we have impact forces, then the factors given in items 3 to 6, it says that it's acceptable, but the impact factor should be included. Okay, and number 9, there's also remarks regarding the brittle materials, and also for number 10, if it says here where higher factors might appear desirable, a more thorough analysis of the problem should be undertaken before deciding on their use. Okay, so those are ballpark values for the safety factors. All right, now let's move on to the failure theories. Okay, so the failure theories, or actually sometimes referred to as criteria or criterion, basically what it says, or the concept, is that can the data obtained from uniaxial tension or compression, or compression test be used to predict failure under more complex loadings. Okay, so this statement is taken from the textbook by Peitel and Cusalas, 2012. Okay, so the textbook is strength of materials. Okay, so again, if we read this when we say failure theories, it's basically the idea is that can the data obtained from the uniaxial tension or compression test be used to predict failure under more complex loadings? So what it means is that if we have this, um, let's say this is our test specimen, and we subject this to uniaxial. So when I say uniaxial, it's just one axis or one direction. So because of this uniaxial, because we subject this to a uniaxial test, then we obtain a graph of the stress strain curve, right? And we have this graph, like for example, uh, we have a ductile material and a brittle material. Okay, stress, strain, stress, strain, and this one is ductile, and this one is brittle materials. Okay, so here in the simple tension test, we have this value right here, right? That's going to be the yield strength, and we denote that as SY. And right here, we denote this as the ultimate strength, SU, ultimate strength in tension, or yield strength in tension. But for brittle materials, such as, let's say, concrete or some cast irons, so we have this fracture only, so that's gonna be SU only, SUT if it's in tension, or if it's in compression, then that's gonna be SU C. Okay, so can this data be used to, let's say I have a part like, for example, a more complex part, or let's just say a simple part, a simple member, but subjected to a more complex loading. So let's say we have axial, we have shear, and we have torsion, and let's say we have moment. So how do we predict the failure? Because because in this uniaxial test, then we know that as long as the force or the applied stresses reaches this SYT, then it will start to yield, or it will start to fail. Okay, and by the way, when we say failure, we mean yielding or fracture. All right, this one, of course, there's going to be fracture right here, but for brittle materials, that's usually the governing failure. Let's say brittle materials, and for yielding, usually this is for ductile materials. Okay, so we have a complex loadings, and recall that we have computed this stress state. For example, we selected the point, the critical point, the most critical point, and we use this concept about the stress state, right? So let's say we have shear and things like that, and then we also did draw the Moore circle, right? So sorry, this one should be the maximum, just to determine the maximum, the shear max, and also the principal stresses right here, sigma 1, sigma 2, and sigma 3. Okay, and the idea is that if this sigma or this principal stresses reach this yield, or reach this ultimate strength, or this let's say the shear max, if it reach the shear yield stress. By the way, there's still another one, that's S sub SY, that's gonna be the shear yield strength. So we'll just have to compare these two, or take the ratio of these two, because this is something like the strength side, because the data right here, like the yield strength or the ultimate strength, that's going to be the strength side, and this will be the load side. Okay, so because of that, then as we discussed earlier about the factor of safety, then we can determine the value of the factor of safety, right? So we have the strength right here, let's say the S, and here the loads, the load side. Or if this one is given and this one is also given, then we can solve for the allowable, or for the design stress, I mean design stress, or the working stress for the load side. Okay, so if this one is given, the N, and you have, since the strength side usually this is obtained from the data, then we can solve for the working stress. Okay, so I guess that's all for this video. We'll continue our discussion in the next video.